Hi, this is Dr. S.P. Harsa from Mechanical and Engineering Department, IIT Roorkee. In the course of vibration and control, we are basically discussing on the isolators. In the previous lecture, we discussed about the design concepts, that what exactly the design strategies should be adopted for suppression of vibrations, irrespective of whether it is a high exciting frequencies or the low frequency excitations or even at the resonant conditions. And then you see what could be the potential location for keeping the isolation, so that the effective isolation can be done in terms of the source isolation or the shielding towards the receiver as well. So, in the previous lecture we have checked various examples. In those we got to know that what is the effective way of doing the isolation, and then whether we need to apply the spring or the damper or the masses to suppress those things. And also you see, along with that, we know that when we are talking about any isolation feature, the perfect isolator can be designed based on what is the insertion loss. So, even we have a discrete kind of systems or we have a continuous system, even we have a steady state feature or the transient feature, or even if we have the impact loading, which is one form of transient only, how we can design the system according to the isolators. So, all these concepts which we discussed in our previous lecture, now we are going to apply these concepts into some of the real practices, and we are trying to solve some numerical problems. So, in the first example, we have an electric motor which is elastically mounted by a way of two identical isolators. 2 millimeter thick steel plate is there, and when the motor is driven, its rotating parts certainly generate the vertically oriented, the sinusoidal excitation forces in between the machine and the joints or which the machine is being settled. We need to find out the ratio between the total force acting on the foundation when we have the isolators, and in other case when we do not have any isolator in between. Along with this, we need to carry out the calculations at low frequency under the assumption that the electric motor, when they are operating, is just generating the steady state harmonic exciting forces with the circular frequency of omega and the amplitude is there. So, we are trying to eliminate right now the transient forces, because if we adopt the transient feature, then certainly the different amount of exciting forces are being coming out on the system. So, just now you see we would like to start from the basic system. So, in this the numerical data are like that: the mass of motor of 100 kilogram, and each isolator, we have basically four isolators at the 4 junctions for complete mounting of the motor, is having a isolator. The complex stiffness which we discussed already in the previous lectures is 1 plus 0.01 iota into 10 to the power 4 Newton per meter. So, as you can see on the screen that we have the electric motor which is elastically mounted on the large steel plate via 4 vibration isolators. Now, this is our physical system. As we discussed in our first lecture, that whenever the physical systems are there, we need to put the spring mass system as a discrete system, like just to analogy of the actual systems are. So, here we have the mass and whatever the exciting forces are, and then you see here this mass which is being rested on this steel plate is having the 4 spring. So, all the 4 spring, since they are in absolutely at 4 junctions, they have the stiffness of 4 K. And then you see here, when we are trying to resolve with the free body diagram according to the forces acting on the system, we have the F excitation which is being applied on top of that, you can see this, and you see whatever the restoring forces which are coming out due to the spring connection. So, we have this, and equal and opposite amount of these spring forces are being acting on the mass as well as on the foundation. So, even if you want to just look at the next diagram, it just shows that how a clear representation of the spring and the restoring forces which are being balanced at both the ends of the springs. So, this is what my system is, and now you see here we need to start to evaluate the losses in that, and you see like what the other parameters are. So, first of all we need to apply some of the assumptions which can differ or which can make rather ease of the calculation from the realistic feature. So, first of all the motor, the source of vibration is to be considered as the rigid body. Second, the foundation, whatever the like the steel flat plate is there, can also be considered as the rigid body, and each isolator, the 4 isolators are there, which is being acted as the spring, is the massless spring. So, when we are considering those things, then it is pretty simple that the inertia forces which are being generated due to the rotation or some kind of oscillation are being there from the 100 kilogram of the machine. So, we have m into d2x by dt square inertia force, which is well balanced by the differences of the 4 cumulative effect of all 4 springs restoring forces and the exciting forces. So, F exciting minus 4 F1 is my force summation, which should be balanced by the whatever the inertia forces are. So, 4 F1 we can say that these are nothing but the restoring forces coming out from the spring in terms of the foundation, we can say. So, 4 transmitted through all 4 isolators, and since we are saying that whatever the excitation features are being coming from the machine to this, because when we are operating the machine from the electric operations like this, the compressor or the pump, we know that whatever the exciting nature of the systems are is always according to the simple harmonic motion. So, with this sinusoidal feature of this, the complex valued displacement can be straightway we can say the eliminated, and the exciting forces becomes 4 F1 divided by the exciting forces F excitation is nothing but equals to 1 minus omega square by 4 k oblique m, because this omega square, which is nothing but the circular frequency of the system excitation, and 4 k by m is coming out from the machine excitations, because here we know that the entire system is supported at the 4 supporters. So, k by m is my natural frequency of the system. So, I can say that this is nothing but equals to 1 minus omega square by omega 0 square to the power minus 1, where omega 0 square is nothing but it is a mounting resonances. So, in this, the first part is just saying that we need to apply the entire equations of these for all 4, we can say the rigid rigid mounting parts, and for the machine, if we have say the endpoints over which the machine is rigidly supported, and they are simply we can say the connector in between the machine and the foundation, and if we have these endpoints, we can say that the first term should be 4, whatever the 4 omega by m is coming on the lower term, it can be replaced by n omega square by m. Means here whatever the number of points are there, accordingly the things are being varied with the stiffness variation. So, in case of no oscillator now, the first case, the force is directly transmitted to the foundation from the machine, and we are saying if this is equals to F excitation, the desired ratio between the force with and without can be just says that Fu and Fm is equals to 1 minus omega square by omega 0 square. So, this is what you see, a direct relation in between the forces which are being applied or transmitted like from machine to foundation, and there is in between we have the springs or not. And we can even define the insertion losses on the basis of this particular formula, that the DL is nothing but equals to 20 log, as we discussed you see in the previous the chapter. The insertion losses are nothing but equals to 20 log of 1 minus omega square divided by whatever the natural frequencies are. So, we can say 20 log 1 minus omega square by omega 0 square, or even we can go with the mobilities, because we know that if the mobilities are high, the isolator is perfect. So, 20 log ym plus yi divided by ym, where ym and yi are nothing but machine's isolator with respect to their mobilities. And we know that this is absolutely applicable not only to the isolators, but also the shielding isolation towards even the receiver end. So, you see here in this particular mathematical description, we could easily figure out that what exactly the ratios of the force is when we are applying the isolation in between the machine and foundation or not. So, there are you see various characteristics are there for the insertion losses, just like the first, when no isolation is being obtained for any exciting frequency, then the exciting frequencies are always far below the mounting resonances, just like in this case. So, we can say that this F0, which is being we can say the exciting frequencies are there, they are always far low than the mounting resonances. Secondly, when the insertion losses takes we can say whatever just on the large or negative values for any excitation which is close to the mounting resonances, you see 4k by m, then we can say that the forces on the foundation which is being amplified even in comparison to the reduction one. So, more and more excitations are there, because it is pretty clear that when the system, when the forcing frequencies, when they are excited and when they are close to the system's frequencies, there is a resonance, huge amount of energies are there. So, the spring cannot handle that amount of excitation level or the energy. So, certainly you see here we need to check it out that the insertion losses are now significant in this case. Finally, large and positive insertion losses can be obtained for those exciting frequency which is well above than the mounting resonances. The insertion loss is asymptotically approaches up to even 40 dB per decade. So, we can see that if the exciting frequency is less than whatever you see we can say the mounting frequency, then certainly you see this is one of the effective way and insertion losses are almost negligible, because this is what the basic physics of the vibration is. When the system is exciting well below the natural frequency, the spring connectors are perfect one. They can straightway absorb the kind of energy, and they can even you see control the oscillation of the vibration, whatever the amplitude is there. But even when the system is exciting at the higher frequencies, or even when the system is exciting at the resonant condition, the insertion losses are quite significant with the spring controllers. So, you can see that the insertion losses for rigid body which is being mounted on the rigid foundation with these in between these things, the mounting resonances can be termed as 2.18 in this example. So, we can see that this is what the insertion loss is, they are being coming down to negative, and then you see here after that when the exciting frequencies becomes more and more, the insertion losses are almost approaching up to the 100 dB you see. So, this diagram clearly shows that at the lower frequency, at the resonant frequency and at the higher frequencies, how the insertion losses are being varied with this, along with the mounting resonances. The deep through the insertion losses at the mounting resonance, its negative value is clearly shows in between the lower frequencies, and the vibration isolation system can now be the counterproductive at the low frequency, and above all it is essential that the exciting frequency not fall in the vicinity of the machine's mounting resonant frequency, otherwise the insertion losses will be of high. So we can conclude from this part that the vibration isolators must be designed in order to prevent the coincidence of machine's mounting frequencies with any other exciting frequencies of the part. Otherwise you see here the things will be of the insertion losses will be of a different nature. Moreover, it is clear that a positive effect is obtained from the isolator at the frequency which are above than the mounting frequencies. This is a great conclusion, and the implications is that as low as possible the mounting resonant frequency should be short. So generally you see here when we are designing these things, the mounting resonant frequency is always keeping in between 2 to 10 hertz band, so that we can avoid this condition in which you see here the insertion losses are of this nature. So this numerical was there for the rigid body and the rigid foundation. Now if you are just taking the flexible foundation instead of the rigid foundation, so when the exciting frequency increases, the deformation of the foundation due to exciting force becomes too large to ignore, because you see here when the deformation of the foundation is greater, certainly the exciting frequencies are of more importance. A model in which the foundation is flexible, we need to use in that. So the number of different modes with the different characteristic frequencies in such cases are available. And if for example the foundation of the system, the entire system in which you see the jaws and everything is there, is to be considered in the dimensions with an infinite plate model, and straight weight can be used to describe the motion of the foundations with the flexible way. And if the foundation exhibits a resonance, then the mass system can be used as a first approximation which simply describe the real character of the systems. So again it all depends on whether you see we are using with only to describe the motion of the foundation, or you see the mass damper is. So in this case you see here now we are again considering the same previous example, and now we are assuming that there is an infinite plate, the same steel plate of joist you see here, and it is a valid model you see of the foundation response with the flexible feature. Now we want to find out the total force on foundation with and without oscillator. So you can see that we have the same, you see the motor you see here which is running at this part, the exciting frequencies are there, the same 4 rigid supporters are there in between the rigid body and the flexible mountings or the supporting, we can say that, and you see the foundation is a flexible one in which you see we have the displacement x2. So when we are applying these things on this, now we need to put the two degrees there. One, at the masses we have, you see, the force balance equation when the inertia forces are being suppressed by the difference of excitation minus 4F1, and the same time this foundation which was ignored in the previous case is simply 4F1, and then you see we have the excitation x2 is there. So you see here in the single isolator, now you can see that we have on top of one end we have one displacement, on bottom of that we have x2 and F1, and this the top force F1 to F1 is to be balanced with the stiffness K. Now we can apply straightway the Newton's law for this, and we know that you see since this elastic deformation is being varied with the kind of the flexible mounting, so Hooke's law can be applied straightway, and the mobility of the plate which is at the yield point can be straightway formed in the equation. So we have m d2x1 by dt square is nothing but equals to this inertia force is being balanced by F excitation minus 4F1, and where the F1 is nothing but equals to the restoring force K into X1 minus X2, and this X2 which is being coming out due to the flexible mountings can be put as I omega inverse Y plate into 4F1. Now we are trying to eliminate the X1 and X2 in such a way that we can get straight away the force relations. So if I am saying that when the isolator is there, so 4F1, and when isolator is not there, then force excitation. This is a very simple thing you see here. When you do not have any isolator in between the machine and the foundation, straight away the exciting forces are being transmitted. But if we have the springs, then 4F1 the force is with the isolator. So 4F1 by 4F excitation is nothing but equals to minus 4K over m omega square divided by 1 minus 4K m omega square plus 4K divided by I omega Y plate. And we already discussed that this is the yield feature of the plate is in that, because we need to apply the Hooke's law at that point. So we can say that it is nothing but equals to 1 by I omega m, which should be equals to Ym, or else 1 I omega by 4K is equals to Yi. So these are, you see, nothing but the two, like as we already discussed in the previous diagram, that you see here we have Yi and Ym, and they are straightway showing here a clear insertion of these. You see that how the machine and the isolator mobilities are being varied. So this machine and like Ym is mobility of machine and Yi is the mobility of the isolator. When they are being varied here, then certainly you see here we need to straightway keep in this part that how the Ym means when 1 by I omega is there, it is clearly showing the mobility of the machine, and I omega by 4K, this is absolutely with the isolator, it is clearly showing the isolator mobility. So 4F with isolator divided by F excitation is nothing but equals to the mobility of the machine Ym divided by Ym plus Yi plus Y plate. So in this you see here we are considering the mobility not only in the machine and isolator, but also the plate, because the plate is acted here as the flexible feature. So without oscillator, if you are just saying the forces on the foundation can be determined by excluding the second term in the equation from the system given equation, so that we can simply set again the 4F without divided by X excitation is nothing but equals to 1 divided by I omega m divided by 1 I omega n plus Y plate, or else we can say that Ym divided by Ym plus Y plate. Yi is now not present. So the insertion losses are quite significant in that case. It is nothing but equals to 20 log Ym plus Yi plus Y plate divided by Ym and Y plate in the case. So if we divide this, then we have the insertion losses, which can also be applied to shielding isolation, is nothing but equals to the previous case. It was 4F with divided by 4 excitation is Ym divided by Ym plus Yi plus Y plate, and here without 4F divided by 4F without divided by F excitation is Ym by Ym plus Y plate. So you see here the insertion losses are of these two parts. So we can simply find the 20 log Ym plus Yi plus Y plate divided by Ym plus Y plate for that. So in that it is pretty simple to calculate those. Now the second point is there, the mobility of a 2 centimeter thick a very large steel plate. So certainly you see here we need to go with the Poisson ratio, and we need to check it out that you see how we can simply adopt like the density, elastic, Young's modulus and Y plate as well. So Y plate into square root of 3 1 minus mu square, mu is the Poisson ratio here, divided by 4 h square rho E, where the rho density certainly we can calculate, that is 7800 kilogram per meter cube. The Poisson's ratio is 0.3, which is pretty common for all the metals. Young's modulus, it is a steel plate, so it is 2 into 10 raised to power 11 Newton per meter square, and then we have h, which is nothing but you see here whatever like the thickness of that is 0.02 meter. So when we are keeping this, we can find the mobility here is 261 into 10 to the power minus 5 meter per Newton second. So here when we are getting those things, the insertion losses leads to the various features in that, and which we are going to show in the next figure. But here few of the points which are to be remembered. One, the flexible foundation, when we are adopting that, straightway affecting the insertion losses in two bands. One, the mounting resonances, and second, the frequencies which are more than the 50 hertz, as the system excitation is at 50 hertz. So you see here, when we have the flexible foundation, in other words, it is affecting the low frequency and higher frequency with respect to the natural frequency of the system. So you can see that this is what the insertion losses are there. When we have the rigid foundation, as far as you see, like the lower part is concerned, you can see what we have a clear feature of that, and it is just going with this. So we have, you see, the rigid foundations towards that. But when you have the, like the elastically mounted, the infinite steel plate, then the things are somewhat more compliant foundations, and you see here at the higher harmonics, the things are becomes, you see, showing the less insertion losses at these points. So this is what you see the basic criteria for designing the isolator with the rigid or the flexible foundation. So as the mounting resonances with these whatever the frequencies are there, the insertion losses increases due to the ability of infinite plate to be act as a more sink energy. That means you see here whatever the exciting frequencies are there of the mounting resonances, the insertion losses are always becomes more significant. But above 50 hertz, the flexible foundation is always provide a significant effect with the lower insertion losses, because of we know that you see when we are going beyond that, the absorption feature is quite significant in that case as compared to the rigid foundation. Hence the isolation obtained is mainly determined by the ratio of isolator mobility to the mobility of the plate. That how you see, like these this particular factor in which the mobility Ym or Yi to the Y plate is varied in this case. But at the higher frequencies, the insertion losses are almost like reaches asymptotically, means the curvature feature at 20 dB per decade, per whatever you see, like the decade rate is there, and it is being increasing feature as we can see. But here when we had the rigid foundation, this was happened at the 40 dB. So this you see, this approach is now drastically reduced to 20 dB only. So this is one of the unique feature when we are adopting the flexible foundation. So compared to an ideal rigid foundation, an amplification peak at the mounting resonant frequency is drastically reduced, and this rate of increase is also with the same insertion losses, and this is one of the great advantage of this. So when you see the insertion losses are being like reduced, it is mainly due to the diminishing the mobility, or we can say the impedance gap between the isolator and the foundation. So when we are saying that like the Yi by Y plate is being reducing, certainly it has a clear impact on the insertion losses. So this is you see like one of the great criteria for adopting the rigid foundation or the flexible foundations according to what the exciting frequencies are there and how the insertion losses are being varied with the compliant support from the isolators. Now we are just going into the another section, that is the wave propagation in isolator. So when we know that we define the isolator, we designed accordingly, but how the wave propagations are being occurred in the isolator itself, and when the exciting frequency is increasing, and this is increasing so much that the deformation field in the isolator is a wave motion. The ideal spring which we are adopting is not at all compatible. So depending upon the isolator design, the various models for these wave propagations in which the isolator is more compatible is always choosing. So now how we can go that? Now we are going to the another numerical problem with this, in which we are considering the machine foundation situation as we have shown in the previous two cases, and now we are assuming that the isolator is a circular cylindrical bar which is undergoing primarily the axial deformation, and for this axial deformation motion in isolator is build up of longitudinal waves. That how you see, like the wave propagations are there, what is the nature of the wave is. And in order to permit the direct comparison between this, what we are going to see, we are going to take the same isolator design, and every isolator is assumed to have the length of 0.05 meter and the cross sectional area is 0.005 meter square. And the material which we can adopt here, having the density is 2500 kilogram per meter square, and you see the Young's modulus of this, which has the complex nature because of the variation, it is 0.1 into 1 plus 0.01 iota megapascal. Now for these input values, the isolator stiffness at the lower frequencies are just matches as we have just chosen in the previous case. So with this now we would like to solve the problem, and we would like to find out that how you see the losses are being occurred in that and how it is effective. So first of all, we need to go with various steps in which we need to make first the block one end of the isolator, that you see whatever the first end of isolator is there, we need to make a proper block, means just blocking that. And by calculating the ratio of force on the blocked end, which we are just blocking, to the excited displacement response at free end, the frequency depending dynamic isolator stiffness is simply being carried out, and it is simply giving that how the frequency dependent parameters are being varied. And if the stiffness in the result you see is just taken with the dynamic stiffness as the another parameter, the insertion loss can be find out for longitudinal wave propagation in which you see the isolator is just feeling like that. Now you see we can compare those things. So here the insertion loss of the isolator is just shown here, and in that you see here we can simply see that whatever the previous two cases in which the stiffness and everything is considered, in the real vibration isolation we can simply see the insertion loss is varying with the low frequency, the mounting resonance frequency, and the higher frequencies are there. So resonance in the machine, for example, say whatever the things are being there, it has the negatively impact on the insertion losses, and that is because the difference in the impedance between the machine and isolator is always reduced with the machine resonances. So you can see that we have the same at the lower frequencies, the insertion losses are being coming down at the exciting frequencies you see here, and then you see it is being at the higher harmonic frequencies it is being increasingly showing the insertion losses. So in that we have the rigid foundation, we have the compliant foundations, this one, and then you see here in this when the wave is propagating, you can see the wave propagation at two different frequencies, the 64 hertz and 130 hertz for this. And this wave propagation, since it has you see the longitudinal feature, since you see this rigid foundation is providing the good support, they are speedy, and you see the nature is just like that. So you see here this which we seen in the three examples, the rigid, the flexible base, both you see here, or else even you see here in the previous diagram when we see that you see how the wave propagations are there, this part which we discussed. Now here if there is you see the nature of machine is of deformable nature, and if it is so, then we can see that how the coordinate directions are being considered with the mass is, because you see till now we considered the point mass of the motor itself, and now we also would like to see the insertion loss, how it is being varied. So the insertion loss is very low because the rigid point mass at the exciting frequency is just near to the mounting frequencies. And if the several the coordinates, we can say the 6 degrees of freedom, the 3 translational and 3 rotational coordinates are being considered here or are being taken, then you see we can see that what are the mounting resonant frequencies and how they are being exhibited here. So in general case, since the 6 critical frequencies are being considered, so we have the 6 different mounting resonances, and every real machine also exhibit the internal resonances at certain frequency. So if you are saying that the first frequency, the first resonant frequency of the machine with say 100 kilogram, as we have considered in the previous diagram, if it is the entire IC engine is falling down from 100 hertz to 500 hertz range, then you see how exactly the deformable machine is playing. So if the machine is composed of the flexibility attached to the various section, the first resonance can of course you see lie at even lower frequencies because of the flexibility provided by the machine itself. And the possibility of this wave propagation in the machine can also affect the isolation insertion loss even with the elastic mountings. But this is all you see depending on the relative stiffness variation of the machine to isolator, because ultimately you see entire things are being varied through these connectors or through these the contact regions. So how the isolator is being varied with this, and if the machine stiffness varies significantly due to any reason, maybe resonances, maybe anti-resonances, then even the insertion loss will also vary accordingly, and it plays a critical role in designing of these isolators. But on an average we can say that the isolation performance is degraded with that, because you see here when you have the flexible machine, then certainly you see here whatever the performance features which are being coming out due to this isolator having a different deformation rate, and the insertion loss is also varied with that. So certainly you see the performance is degraded with the first resonance itself. So the insertion loss for these flexible machine can also be see in that particular diagram with the internal resonances, and even when the foundation is rigid and the isolator is you see the same as we adopted that. So this diagram is clearly showing that how the insertion losses are being varied for the machine which is being mounted on the even the elastic mountings, but with you see the internal insertion in the machine, there are you see the greater affected area at the lower frequency, and on the right hand side you see we can see that how the arrangements are there. So if you look at the insertion losses of this figure, we will find that the insertion losses at the lower end is somewhat showing the internal the resonances, and when it is approaching to the mounting resonances, certainly we have this feature, and when you see we are going towards the higher order frequencies, there are two things: the rigid machine structure, which is again showing the similar kind of insertion losses, and it has a linear propagation. But when we have the internal we can see the resonances with machine structure, you can see that after even the 100 hertz or even after the 50 hertz, the nature of the insertion losses are being varied in a drastical way. Why? Because we know that when the system is exciting at the higher harmonics level, and since our machine is also showing the flexibility in those cases, then certainly you see here we cannot effectively control the insertion losses, and the variation will be of drastic level. So you can see that how the variations are there with the internal resonances. So in this case, as you see here, when we are just simply like showing these things, even on the right hand side you can see that we have a clear arrangement of the masses, the different masses. Say we have 15, 20 kilogram, 15 kilogram, even 25 kilogram and the 50 kilogram. We know that the stiffness of the spring which is being required here is 50 into 1 plus 0.1 iota Newton per meter. And when the excitation is there, you see this is what my machines are, and when the excitation is there on that, the internal resonances of the entire feature, you see this feature is critically playing in the design of the isolator. And you see, if the appropriate isolator is not being chosen, certainly we have a different kind of insertion losses. And you see this mechanical model of machine is clearly showing that how the transmissions are there through these springs or through these connectors, and we need to choose appropriately the stiffness of these isolators are, so that the proper transformation can be taken place with the flexible machine. So in this case, you see here in the entire chapter we mainly discussed about the three different cases. Like you see here, if we have first the rigid base, means the foundation is rigid. If we have the flexible foundation, and now if we have the flexible machine. So in flexible machine case, we can certainly go towards the main conclusion that the machine has the resonant frequencies as I shown there, 150, 245 and 525 hertz, and the anti-resonances according to the resonance features is 160, 205 and 495 hertz. And that figure shows that the resonant frequency exactly, the machine is compliant, and there are, you see, the minimum insertion losses are there. That means the frequency at which the isolations are just poor. So when we adopt these things, we know that how the isolators can be designed and what could be the possible, the resonant frequencies are there. But in other hand, you see, if the extra isolation is obtained at anti-resonances, we need to see that the machine is not the flexible one, the machine is even more stiff. And for increasing exciting frequency in the region which is above than the first machine internal resonances like 5 to 10 hertz or all, this average insertion loss is drastically false of the feature. So we need to check it out that you see here what is the the machine foundation, and you see here the this internal resonances are there and how the corresponding exciting frequencies are being varied with this. And this effect which is coming due to this machine foundation can also be smaller with the unsprung mass, and that is taking, you see, more of the care when the entire motions are there in the just highly, or we can say the rapidly feature with these isolators. So in these formations, now we could easily figure out that when the machine is acted as the flexible feature exactly just at the contact point, or when the foundation is occur at the flexible feature, then certainly there are different insertion losses, and when we are designing the isolators in between these flexible features of machine or foundation, we need to check it out that how the insertion losses are being varied at the lower frequencies or at the higher frequencies, or even exactly when these frequencies are mating with the internal resonances. And this is one of the drastic criteria. When the frequencies are mating with the internal resonances, the insertion losses are always being drastic there. So in this lecture, you see, we discussed mainly about the foundation feature and appropriate isolators according to that, the foundation or the machine, rigidity or flexibility of these two features. In the next lecture, our main intention would be focused on that how we can check the insertion losses especially when we are designing the isolators for various different applications. When you have a steady state, the continuous operations of the forces means you see the continuous dynamic features are there, or the dynamic stiffnesses are being like playing in that. And also you see here, when the continuous loading is there, it's very simple to find out the frequency range according to the insertion losses, and appropriate, we can say, the mobility or the impedance can be chosen for that. And we know that when the difference between the impedance and mobility is high, the isolator is working in a very perfect way. But at the same time, you see, we are also going to discuss in the next chapter about the shock loading. When the abrupt energy is coming to the system, then how the isolator is going to work. Because ultimately, the effectiveness of the isolator is absolutely based on, when the energy is coming, how much time will it take to release that energy according to the performance criteria. So as far as these common examples are concerned, there is no problem with that. Once you have chosen the isolator, whatever the energy excitation is coming, it's of a continuous nature because of the harmonic excitation, and we can certainly find out the way to release the energy, and based on that the performance can be immediately evaluated. But when the energy is coming in the shocking feature, so sudden impact forces are there, impulsive nature is coming, then how we can design the isolator so that the energy can be restored for maximum time period, and then you see slowly it can be released so that we can maintain the steady state feature. Because till now you see, we only discussed in all the numericals the steady state responses, even the force excitation or the displacement outcome will be taken care. But when you see the transient nature of the force is being acted on the system, then how the system is going to respond, how we can effectively measure the performance of the isolator, or even other way, how we can design the isolator based on the insulation losses, the insertion losses can be checked out. Thank you very much.